All right, welcome back. This week, we're going to be talking about volcanoes and earthquakes. So, our goals for this lesson are for you first to understand how scientists use theories, with the example of plate tectonics theory, then to be able to explain how tectonic processes cause volcanic and earthquake hazards, and then finally to explain why hazards like volcanoes and earthquakes have different impacts on different communities. So let's start with the idea of a theory. So the everyday meaning of theory, the way that you might use it in your typical life, it means something like a guess or a proposal. It shows that you're uncertain about something. So you might have a theory about, why your pet is acting the way they are. You might have a theory about what's going to happen in your favorite TV show. And these are, when you call it a theory, you're saying, I might not be right. This is just my best guess at this. But that's not what scientists mean when we talk about a theory. So this is another case, just like we mentioned the idea of work, that when scientists talk about work, they're not meaning the exact same thing that you and I might mean in everyday conversation. Theory is another one of these words that it means something a little different when scientists use it. So this everyday meaning of theory, if this were something that were testable, if we can come up with a plan to figure out how to verify or falsify your theory, then a scientist would call that a hypothesis. That a hypothesis is a guess or a proposal that we can then test to see if it is correct or not. When scientists talk about a theory, they mean a well-supported explanation of how something in the world works. So I've got there the definition that is put forward by the AAAS. That's the American Association for the Advancement of Science. It is one of the largest scientific bodies in the United States. It encompasses scientists from all different disciplines. And they say that a scientific theory is a well-substantiated explanation of some aspect of the natural world based on a body of facts that have been repeatedly confirmed through observation and experiment. So when scientists say something is a theory, they mean that we actually have a lot of good support for this and that it helps us to explain what's going on in the world. So there's two important elements: that a theory has explanatory power. It helps us explain why things in the world are the way they are, why they function the way they function, and that it has evidence that supports it, that has been repeatedly tested and confirmed. And when we have a theory, we can use that theory to help us generate hypotheses. We can say, well, if this theory is true, then that means we should expect to see this certain thing. And then we can go test that. We can see, do we see things working the way that the theory says? And by testing those hypotheses that come from the theory, we can then confirm, refute, or in most cases, refine the theory. So we can take a general theory and we can work out the exact implications of it by generating hypotheses about how that theory will manifest in certain places or in certain sorts of scenarios. So in a scientific context, saying something is a theory is to say that it has a lot of support to it. It's not just a theory. You may hear that expression, just a theory. That is an expression that applies to the way we use the word theory in everyday language. That doesn't apply in a scientific context. A scientific theory is not just a theory. It is, in fact, a well-supported thing that we know about our world. So the theory that we're going to look at in this lesson is the theory of plate tectonics. And plate tectonics is essentially the unifying theory for the discipline of geology over the last half century, since this theory was fully worked out. And so in that sense, it kind of parallels the role of the theory of evolution in biology. So evolution helped biologists to understand how all these different aspects of living things fit together. So every different subdiscipline of biology is able to draw on evolutionary theory to help explain the specific things that they're studying. And the same kind of thing holds with plate tectonics and geology. So I've got a diagram there that shows plate tectonics feeding into all these different subdisciplines of geology. So we have geomorphology, which is the study of landforms. Why do we have this shape of hill here and this shape of valley? Well, plate tectonics helps us understand why those landforms look like that and are located where they are. We have mineralogy, which is the study of how minerals, the tiny crystals of minerals, form, and petrology, which is the study of how those minerals are built up into rocks. And so to understand how minerals and rocks are formed and why a certain kind of mineral or rock forms in a certain place, plate tectonics really helps us to understand how that happens. We have paleontology. If we're studying the history of organisms going back through the history of the Earth and why we have certain kinds of fossils of certain organisms in certain places, plate tectonics helps us to understand that. And that's kind of the intersection then of geology and biology, because of course the theory of evolution is also helpful for understanding paleontology. We've got resource geology. So that's the branch of geology that helps us figure out where to find natural resources. So we're looking to drill for oil or mine gold or extract lithium or whatever geological resources we're interested in. Plate tectonics helps us understand where we're going to find what quality of deposits of which resources that we're interested in. And then the subfields that we're going to look at in this lesson are volcanology, the study of volcanoes, and seismology, the study of earthquakes. And both of those fields draw very directly on the theory of plate tectonics to help us understand why volcanoes and earthquakes happen in the way they do. So this is a theory that brings together all these different aspects of geology into one unifying framework. And so that's why we call it a theory. It gives us an explanation for lots of things, and it's being constantly tested by scientists working in all these different disciplines. So the geomorphologists are constantly finding that plate tectonics is helpful for them to explain the landforms that they're trying to account for. The petrologists are constantly finding that plate tectonics is helpful in understanding why this kind of rock exists in this place. The resource geologists are constantly finding that plate tectonics helps them understand why is there a gold deposit here that we could mine for. So this theory is constantly being used and confirmed and then further refined by work done in all of these subfields of geology. So let's look at how this theory came about. So we can trace this back to the beginning of the 20th century. There was a German geologist named Alfred Wegener, and he proposed that the continents have moved across the surface of the Earth. So before his time, it was generally believed that the continents on the Earth had always been in more or less the same locations that they are today. And so, maybe water levels have gone up and down so that, certain parts would get flooded or certain things that are now underwater might get exposed. But the core of the land masses, it was believed, had been in the same place because, the Earth is solid. How could things move? But Wegener came along and he said, no, these continents have moved across the surface of the Earth. And he referred to this idea as continental drift. And he had two main pieces of evidence that he put forward for believing that continental drift was a real thing. The first one was to just look at the shapes of the continents. He said, you look at the shapes of the continents, it looks like something can fit together like puzzle pieces. And probably a lot of you might have noticed that if you look specifically at the coastlines of South America and Africa. It's a really clear fit between those two continents. They look like they could go together like puzzle pieces. Other continents aren't quite as obvious, but it gets to be a much clearer fit if you're looking not at the present day shoreline, but at the geological edge of the continent, which is some distance offshore. If you look at the geological edge of the continent, then you can find these things kind of fit together like a puzzle that's been broken up. Second, he pointed out that there are rock formations and fossils that line up once you fit these continents together into this puzzle. So there may be fossils of a certain species that are found in eastern South America and in western Africa. And so if those continents had always been where they are, it would be a little surprising. Why is this organism found on both sides of the Atlantic Ocean? How did it get across there? You also find rock formations where you'll have a certain type of rocks with a certain orientation of the rocks that will run right up to the coast on one continent, and then you'll see the exact same thing on another continent, and those rock formations match up exactly if you fit those continents together as if they had been one and broken apart later. So these kind of continuities across the gaps between continents suggested that, well, maybe those continents had been connected together in the past and then had broken apart. So these were the pieces of evidence that Wegener was pointing to support his idea of continental drift. However, one thing that he didn't have was a mechanism for how does this happen? How would continents move across the Earth? What happens to the crust of the Earth when a continent moves into a new place? And Wegener didn't have a good explanation for that. He also couldn't say, what's the force that's moving this? It would take a lot of energy to move an entire continent, hundreds and thousands of miles. How is that? Where's that energy coming from? What's the force that's pushing this? And Wegener didn't have that explanation. So geologists did not immediately sign on to this idea. It didn't immediately become adopted as a theory because it was an intriguing idea. There was some evidence in favor of it, but it was incomplete. We didn't have a good understanding of how this would work and how you could explain what's happening. But because this was an interesting idea, people continued to look for more data. And by the middle of the 20th century, we had found some important data that helped us to add that missing mechanism to Wegener's hypothesis about continental drift. One of the key pieces of data that we have is data about the age of the sea floor. So in Wegener's time, we had barely begun to explore the floor of the ocean. We had very, very little information about what was actually down there, what the rocks were like at the bottom of the oceans. But as the 20th century progressed, we got more and more of that information. And we found something very interesting when we looked at the ages of the rocks on the ocean floor. We found that if we take the Atlantic Ocean as an example, because it's kind of most clearly illustrated there, we have the mid-Atlantic ridge that runs down the exact center of the Atlantic Ocean. And if you measure the rocks right beside the mid-Atlantic ridge, they are brand new. They have just formed. But then as you get farther away, as you move east and west away from the mid-Atlantic ridge, those rocks get steadily older and older. They get older and older and older until the oldest rocks are the ones that are right by the edge of the continents. So we get this nice pattern of new rocks in the center moving out to old rocks at the edge. And so this shows us that we could explain the splitting up of continents on either side of the Atlantic by saying, well, you get this, the gap is filled by the formation of new rocks. And that seemed to neatly be able to explain what was going on there. Then we also had seismic data. We could look at the waves produced by earthquakes, and we could see how those waves reach different parts of the Earth. We have very sensitive seismometers that can pick up very tiny earthquake vibrations that a person can't feel. You can't tell that there's any shaking at all, but you're getting these tiny little vibrations from earthquakes all over the world, constantly being detected on the opposite side of the world sometimes. And so by looking at how those waves propagate through the Earth, we were able to start to piece together what the interior of the Earth looks like. And so I'm going to come back to talk about that a little more later when we talk about what the seismic waves actually are. But the key thing is we started to get a sense of what's actually inside the Earth. And our understanding of the interior of the Earth helped us to further explain how continents could move across the surface. And so as we started to piece together this additional information, we went from this idea of continental drift to a fully developed theory of plate tectonics. And so once we had the theory fully developed and we could see how this explanation of the world works, and we could see what its consequences would be and how it lines up with our data about a variety of aspects of the Earth, then this became accepted as a theory, a well-substantiated explanation of something in the natural world that's supported by a lot of lines of evidence. So let's look at that interior of the Earth to help us understand what's really going on when continents move around the world. So our Earth is made up of a set of concentric layers. So here this diagram is showing kind of like a pie slice out of the Earth to show what the different layers are. And so we can start with the outermost layer, which we call the crust. And this is the only layer that people have ever directly visited. So even our deepest wells and mines have remained within the crust. So all of our evidence about the deeper layers of the Earth is indirect evidence. We are looking at stuff that came out of the interior of the Earth. We're looking at ways that data like seismic waves have passed through the interior of the Earth. We haven't, directly been down there to observe it. So the crust is, anywhere from 0 to 100 kilometers thick. So at that mid-Atlantic ridge where the new crust is being formed, it is extremely thin. Other places, it is very thick. And you'll see in this diagram that there is a clear distinction between the crust that is underneath the ocean and the crust that is underneath the continental land masses. So the part of the crust that's under the ocean you'll see there is very thin. So it's very thin. It's also very dense. So we've got this thin, dense layer of rock on the floor of the ocean. Then we've got a much thicker and less dense rock in the crust of the continents. So the continents and the oceans are geologically different. It's not just that some areas are low enough in elevation to be full of water. So we actually have different kinds of crust in the continental areas where it's very thick and less dense, and then we've got thin, denser crust underneath the oceans. So that crust is made out of solid rock. And so, you can see the crust of the Earth anytime you see some rocks. They're solid. You're seeing the crust of the Earth. Underneath the crust, we have a layer called the mantle. The mantle goes down to about 2,900 kilometers. So it's from the crust down, almost 3,000 kilometers into the Earth. And the mantle can be divided into several sub-layers. So the very topmost layer of the mantle is also solid. It's solid just like the crust above it. And so we often talk about the crust and the uppermost layer of the mantle as the lithosphere. So litho, Greek for rock. So the lithosphere is the crust and the upper part of the mantle, and it's defined by being made out of solid rock. The distinction between crust and upper mantle within the lithosphere is based on the chemical composition of the rock. So we got a different kind of rock, different chemical makeup of rock in the upper mantle, but it's still structurally the same as the crust. It's still solid and fixed to the crust. So we talk about the crust in the upper mantle as the lithosphere. But then we get to the middle layer of the mantle, and it's something called the asthenosphere. And the asthenosphere is critical for how plate tectonics works because the asthenosphere is not solid. It is a molten layer. It's not liquid. It has, it's very viscous. It's more of like a tar-like consistency. So the rocks there can flow and move because they are so warm. We talked in an earlier lesson about geothermal energy, where we're tapping into the heat that's coming from the interior of the Earth. The farther down we go, the hotter it gets. And so you get down to the asthenosphere, it's hot enough that those rocks are no longer fully solid. They're able to stretch and flow and move. So our lithosphere is essentially able to slide around on top of the asthenosphere because the asthenosphere is molten, it's mobile. Below the asthenosphere, we have the lower layer of the mantle that is solid again, because even though it's even hotter than the asthenosphere, the pressure there crushing down onto it from higher layers, pushes all the molecules together and solidifies it. Then below the mantle, we have the core. And the core is made up of two layers, the outer core is liquid. So there the rocks have gotten so hot that they have become liquid. And then the innermost core is solid, once again, due to the pressure down there. So then, and the core is again defined by the chemical composition as well. We have a lot of very heavy metals that sank to the center of the Earth when the Earth was forming. And so now our inner core is basically like a giant lump of iron, and it can spin around inside the liquid core, and it generates our Earth's magnetic field. So if you ever use a compass and it points you north because of the Earth's magnetic field, that's a result of this giant lump of iron in the center of the Earth, the solid inner core that creates a magnetic field. So we've got these different layers, and for the purposes of discussing plate tectonics, we're really focusing on those upper three. We've got the crust, the upper mantle, those two together we call the lithosphere, and then we've got the asthenosphere below that. And those layers are the key players when we talk about plate tectonics. So the lithosphere, this outermost solid part of the Earth, is broken up into about 15 major chunks. So rather than being a solid shell on the Earth, it is split up into pieces that can move in different directions relative to each other. And this is actually something fairly unique about the Earth. We now know enough about the geology of the other rocky planets that none of them have tectonic plates. They all have a solid outer layer, but it does not appear either currently or in the past to have ever been split into plates that move in different directions like this. So if we're looking at the geology of Mars, Mercury, Venus, the moon, none of these places have plate tectonics. So plate tectonics is a sort of special thing about the Earth. Maybe we'll discover some exoplanets with plate tectonic processes happening sometime in the future, planets around other stars. But it's pretty unique to Earth, so that our lithosphere is broken up into these 15 major sections. Then there are a whole bunch of little ones that are kind of wedged in between them, and there are some like major cracks in some of the big ones. But we've got these different sections, and they can move in different directions relative to each other. So they can move away from each other, towards each other, past each other, depending on their interactions with the asthenosphere. So we have currents moving within the asthenosphere, convection currents. So just like we have differences in heating in our atmosphere that cause our winds to blow, these currents evening out the heat, we have currents moving in the asthenosphere. We also have pieces of our plates that are getting pulled down into the asthenosphere. They're sinking down in, or they're getting pushed by material from the asthenosphere coming up. So the interaction of the plates with the asthenosphere is moving them around in different directions. And so if you look at the map there, you'll see that we at Slippery Rock are on the North American plate, which covers most of the North American continent, as well as a big chunk of the Atlantic Ocean, the Arctic Ocean, even a little piece of Russia is on the North American plate, and we are generally moving westward. So the North America and Europe are actually getting a few millimeters farther apart every year because the North American plate is moving westward, the Eurasian plate is moving eastward. We're at a rate of a few millimeters a year. We're actually getting farther and farther from Europe, but then closer and closer to Asia, since as we come around the other side of the Earth. So because we have our lithosphere broken into these plates, we've got a lot of interesting stuff happening at the boundaries between these plates. So a lot of our key tectonic processes are things that are happening at plate boundaries. And we can define these plate boundaries based on the relative motions of the plates at that location. So we talk about boundaries being either convergent, divergent, or transform. So a convergent boundary is where two plates are coming together. They are converging. Convergent boundary, two plates are coming together. And so when that happens, something has to be done with all of that lithosphere. So that either has to get pushed up to form a mountain range, so it gets piled upward, or one of those plates gets dragged down into the asthenosphere and gets melted away. So As a piece of the lithosphere gets pushed down into the asthenosphere at one of these convergent boundaries, it's going to get heated up and it's going to melt into the asthenosphere. So we have a convergent boundary where we're going to destroy some of our lithosphere as those plates push together, and we can have a divergent boundary where the plates are moving away from each other. And so at a divergent boundary, we're going to have to make new lithosphere to fill that gap, because we're not going to have just a big hole looking down into the asthenosphere. Molten material from the asthenosphere is going to come up, and it's going to cool and solidify and create new lithosphere above it. And so that's what's happening at that mid-Atlantic ridge. Since Europe and America are moving away from each other, those plates separate in the center of the Atlantic, and new material, molten rock from the asthenosphere, comes up to the surface, hardens, and forms new lithosphere. And that's why we can measure the age, and we find that the rocks that are right there by the mid-Atlantic ridge are very young. They've just formed, and then they get older as they get farther away. So convergent plates are coming together, divergent plates are splitting apart, and then we have transform boundaries where plates are moving past each other, side to side. So if we have one going north and one going south past each other, or east to west past each other, that's transform boundary. So at a transform boundary, no new lithosphere has to be created, none has to be destroyed. It just got these two plates kind of scraping past each other. Okay, so when these processes are happening, we can get earthquakes, because these plates are not moving smoothly over the earth. We're talking about giant chunks of rock, and that rock is solid and it will get stuck, and pressure will build up. So the various forces in the asthenosphere are trying to move these plates, but they get stuck. They get hung up on each other. They're pressing against each other or getting caught as they're sliding past each other. And that pressure will build up until it suddenly releases and things jump forward a little bit. Okay, so we get that pressure builds up, nothing is moving, but it's getting pushed and pushed and pushed until finally it breaks and jumps forward. And that is an earthquake. So an earthquake is the sudden movement of the earth along a fault. A fault is simply a fracture in the lithosphere. So anywhere you have a break in those rocks where they can move in whatever direction relative to each other, that's a fault. And so at a fault, that pressure can build up for a while, and then the rocks kind of jump forward, and you get an earthquake. You get a lot of shaking happening when that pressure is released there. And if you think back to our lesson about energy, essentially what we're doing is we are building up elastic potential energy. Right? These rocks are under stress. They're being pulled or compressed. Right? So they're under this strain. They've got this potential energy building up, and then that turns into kinetic energy as they finally move. So we've got different forms of energy being transformed here with an earthquake. When we talk about an earthquake, we can locate it based on its focus and its epicenter. So the focus of an earthquake is the location where the movement originates. So the spot that the movement happens, and from which all of the other motion, the shaking and waves, spreads out. And that focus will be somewhere along the fault. So somewhere along this fault, this fracture between two different pieces of the lithosphere, we're going to have the focus of the earthquake. The focus could be deep underground. So the spot where the movement begins might be, miles and miles below us. And the fault is not necessarily nice and vertical. Faults are often tilted, sometimes pretty severely tilted. So the point on the surface of the earth directly above the focus, we call the epicenter. So epi means above, so epicenter, above the center. So the point on the surface of the earth directly above the focus is the epicenter of the earthquake. So the epicenter may not be at the same place where the fault intersects the surface. So on this little diagram here, you see there's a fault scarp. That basically means kind of a steep hillside or cliff that you sometimes see where a fault meets the surface. And you see the epicenter is a good distance away from the fault scarp because the focus of this earthquake happened deep underground and that fault is tilted. So the epicenter directly above the fault is not located on the same spot where the fault meets the surface. But the focus of the earthquake, the origin of that movement, is on the fault. So if we look at where earthquakes occur around the world, we can see that they're not distributed randomly. We have essentially lines across our Earth where those earthquakes are happening frequently and are typically very large. We have other places where earthquakes are rare or non-existent. And looking at this map, some of those lines may look a little familiar to you if you remember a few slides ago when we looked at our diagram of tectonic plates, because those plate boundaries are some of the major faults on our Earth. So the major breaks in the lithosphere are occurring at the boundaries of those tectonic plates, right? The boundary of tectonic plate is a big crack, a big joint in the lithosphere, and so earthquakes are going to happen along those plate boundaries all the time. And so here in the United States, you can see lots of earthquakes right along the West Coast because we have a plate boundary right along the West Coast of the United States, where we have the Pacific Plate and the North American Plate meeting, and so we get lots of earthquakes at that boundary. But you'll see that not every earthquake is right at a plate boundary. We've got a smattering of them in the middles of plates because plates can have additional faults in various spots within the plate. So there can be additional smaller cracks in the plate, and the whole plate is experiencing the forces from plate tectonics. So as the whole plate is being pushed or pulled in a certain direction, that force is being applied to the whole plate. And so smaller faults that exist within the plate can also experience earthquakes. They experience them less often. They're generally smaller earthquakes with less shaking going on, but you can, in theory, get earthquakes lots of places farther from the plate boundaries, but the largest and most common earthquakes are along those plate boundaries, where those plates are trying to move in various directions, and they get stuck, and they build up that elastic potential energy for a while until they finally sort of release it and jump forward a little bit. So we've been talking about earthquakes in terms of the energy involved, and in fact that's how we measure the size of earthquakes, is by looking at the amount of energy released during the earthquake. And we describe this using the moment magnitude scale. So the moment magnitude scale, or we just might say the magnitude of an earthquake, is a measurement of how much energy was released. And this is a scale that was developed to replace the Richter scale. So you may be familiar with people talking about measuring earthquakes on the Richter scale. The Richter scale is an older and less exact version, so it's a similar idea, but the moment magnitude scale is kind of the updated scientific version that more exactly correlates to the amount of energy released in an earthquake. So we're going to talk about earthquakes in terms of their magnitude rather than their measurement on the Richter scale. So the magnitude of an earthquake is on the scale that runs from 0 would be no earthquake, no movement, no energy released. And then the largest earthquakes that we've ever had on Earth get up into something around 10 magnitude. And this is a logarithmic scale. So what that means is that each step on the scale goes up by a factor of 10. So a earthquake that has a magnitude of 5, and then you have an earthquake with magnitude of 6, the 6 magnitude earthquake has 10 times the energy of the magnitude 5. So going up 1 on the moment magnitude scale multiplies your energy release by 10. And then if you go up another one, so your magnitude 7 earthquake would have 10 times the energy of the magnitude 6, and therefore 100 times the energy of the magnitude 5. So you're multiplying by 10 every time you go up 1 on the moment magnitude scale. So that's what we mean by it's a logarithmic scale, is that each step you go up multiplies you by 10. There's also an inverse relationship between the magnitude of earthquakes and their frequency. So we have a lot more low frequency earthquakes and very few high frequency earthquakes. So for example, in the 21st century, so since the year 2000, we have only had 2 earthquakes that were a magnitude 9 or above. So there was one in 2004 in Indonesia that caused the Boxing Day tsunami, one of the most devastating tsunamis that the world has ever experienced. And there was one in 2011 in Japan that also caused a tsunami and destroyed the Fukushima Daiichi nuclear power plant. So that had sort of a cascade of disasters. You have an earthquake, which caused a tsunami, which caused a nuclear plant meltdown. Those are the only 2 that have been 9 or more over the last quarter century, whereas earthquakes that are magnitude 1 or 2 happen constantly. You can't feel them because a earthquake needs to be about magnitude 4 or so before a person can really feel it. Anything smaller than that, we can't feel the shaking of that energy, even if we're standing right on the epicenter of it. But our instruments can detect it. We have seismographs that are recording vibrations of the earth. They can record these very tiny earthquakes that are happening, but a person wouldn't feel it until it gets to be about a 4. And then, of course, the bigger it is, the more energy is being released, and the more damage it has the potential to do, but also the rarer that it's going to be. So the energy release in an earthquake takes the form of seismic waves. So in a previous lesson, we talked about electromagnetic waves. So these are waves moving through the electromagnetic field. Seismic waves are an example of mechanical waves. These are waves moving through matter. So matter is the medium through which these waves travel. And there are several different types of waves that are set off by an earthquake. And these different kinds of waves move at different speeds. And the exact speed of any wave is going to depend on exactly the medium it's moving through. What kind of rock is the wave passing through? That will affect its speed. So unlike electromagnetic waves that we expect to move at the speed of light, seismic waves move at a variety of different speeds depending on the nature of the wave and the nature of the medium that they're moving through. So the first wave that will hit most places, unless you're standing right at the focus of the earthquake and all the waves start at once, but usually the first wave that will reach you because it's moving fastest is what we call a P wave, P for primary, and that's a wave that involves compression and expansion of the earth. So the earth is squishing and stretching as it goes, and those waves can move up to 5,000 meters per second. So these are extremely rapid waves moving out from the focus of the earthquake. Following the P waves, we get S waves, so S for secondary, and these waves have an up and down or side to side motion. So you get hit by the P wave, and then you get hit by the S wave following after that. Then the next slowest wave is the Rayleigh wave, which is a rolling motion of the earth. So it's similar to the way that waves on the ocean have this rolling kind of motion. And then the final wave that will hit you, the slowest of our types of seismic waves, is called the Love wave. That's named after Dr. Love that discovered them. And this is a horizontal surface movement. So the farther you are from the focus of the earthquake, the more separated these waves will be when they hit you because they're moving at different speeds. These waves will also lose energy as they go. So at a certain point, you're far enough away that you're going to stop being able to feel it, but our instruments can pick up these waves as they spread around the entire Earth. So we have instruments that are able to pick up seismic waves generated by earthquakes on the opposite side of the Earth. Way too small for a human to feel, but our instruments can pick it up. And that has turned out to be really useful for understanding what's going on inside the Earth, because the waves are going to try to be coming to you through the center of the Earth. So here we have an example. We put the epicenter of our earthquake on one side of the Earth, and then we can see how these waves move through the Earth. And here we're just looking at the P and S waves. Those are usually the most important ones that get measured. And those waves are moving at different speeds through different kinds of materials. And as they hit changes in the material, they get bent or they get blocked. So this is kind of similar to the illusion with the straw that's broken that we talked about when we were looking at electromagnetic waves, that those waves get slowed down different amounts by air versus water. And so it gives you that illusion that your straw is broken. The same thing is happening with seismic waves. As they pass through the Earth, when they hit differences in the material, so like when they go from the solid part of the lower asthenosphere to the liquid outer core, and then into the solid inner core, that is going to both change their speed and it's going to deflect them. It's going to bend them as they hit this change in material. And so if we take one earthquake and we look at when the waves reached instruments measuring seismic waves all around the Earth, and we look at how strong those waves were when they got there, we can then infer what kind of materials they were passing through. And that's one of our major sources of information about the interior of the Earth. If the Earth was solid and homogeneous, same material straight through, then those waves would all just go straight across to every different point of the Earth. But since those waves are bent, they're delayed, they get reflected, and sometimes there are certain zones where no waves make it through at all, then we can infer that there's these different layers inside the Earth that are reshaping how these waves are moving. So let's now look at some of the hazards that you face if you get hit with an earthquake. What is it actually going to potentially do to you? So one of the most obvious ones is falling. So you can get hit with falling debris, things fall off your shelves, your furniture falls over on you, or you yourself fall down due to this shaking. And so that's why they recommend if you do experience an earthquake, try to get under a door frame, because the door frame is going to essentially protect you from things trying to fall on you. You also have the total collapse of buildings and other infrastructure. So a whole building can fall down, and that destroys the building, which is bad, and also can injure or kill or trap people who are inside the building. Other infrastructure, bridges, are often very severely damaged in earthquakes. So we've lost the bridge. It could potentially kill or hurt anybody who was on the bridge at the time. It also now has cut off transportation. So places that have been hit by earthquakes often find it hard to get things like food and water in for the people that are there if the bridges that stuff might have been brought in on have been collapsed by the earthquake. We can get hydrological changes. So because that earthquake is moving parts of the Earth, that can do things like upset the course of a river, can divert a river into a different course. It can break what's holding back the water in a lake, whether that's a dam, like an artificial lake, or a natural lake, and there's a hill that's keeping that lake full. If that gets shifted, moved, cracked in the process of the earthquake, that could drain that lake, which then, number one, in the immediate sense, could create a flood that could hurt people. And then in the longer term, you don't have your lake anymore if it has drained. And that can have long-term ramifications for things like water supply and fishing that might have happened on that lake, etc. So it can rearrange the hydrology if those things move. And an earthquake can set off a tsunami. So if an earthquake occurs under the ocean, depending on exactly the type and angle of the shaking and how it has transported through the rock layers from the focus up to where the water is, that those waves can turn into a massive water wave, which then spreads out and slams into coastal areas and can do enormous damage, because these tsunamis can be dozens of feet tall, and they come in with a huge amount of energy behind them and wipe out whatever's on the coastline there, kill people, destroy homes and infrastructure, etc. And you sometimes hear people referring to tsunamis as tidal waves, but that is not a great term to use because tsunamis have nothing to do with the tides. Remember that the tides are caused by the gravity of the moon, whereas tsunamis are caused by underwater earthquakes. And the picture that you see there is of some of the flooding that was caused in Thailand by that Boxing Day tsunami in 2004. So there's a big earthquake under the water off the island of Sumatra in Indonesia, and it created a tsunami that slammed into the coastlines all around the Indian Ocean and caused massive amounts of damage, and hundreds of thousands of people were killed from it. So what could we do about this? Well, one thing we can do is have better building codes. So standards for how we build our infrastructure, because we know a lot about how to engineer buildings and bridges and so forth so that they will take less damage during an earthquake and that they'll be less dangerous to people inside them, so that they won't, collapse and kill people, even if they aren't, fit to stay after the earthquake. It'll keep the people in them safe. Likewise with bridges, so they won't just fall and kill anybody that was driving over that bridge at the time. So if we have those building codes in place, if we invest the money to build things in an earthquake safe way, we can reduce a lot of the damage caused by earthquakes. And then there are also early warning systems. So for the earthquake itself, we actually are not really able to predict an earthquake far enough in advance to be truly useful to people. By the time a message about an impending earthquake would get to anybody, it's too late. The earthquake has already happened. And various people are hard at work trying to find ways to predict earthquakes well enough in advance that people can take precautions. So far, we haven't gotten there. We don't have the ability to warn people very far in advance of an earthquake, but we can warn people in advance of a tsunami, because a tsunami will often travel thousands of miles across an ocean basin to hit people on the opposite side. And so we do have tsunami warning systems. So when an underwater earthquake is detected that looks like it could possibly cause a tsunami, warnings go out to places that are on the coasts of that body of water, warning people to take shelter, get away from coastal areas if there's a concern that a tsunami might start. And of course, once we detect an actual tsunami coming, then we can strengthen that warning and even give people an ETA. How long is it going to take the tsunami to get to you? So we have early warning systems for tsunamis. Unfortunately, we're not there yet on earthquakes. So on that map, you saw that in the United States, most of our earthquakes happen along the West Coast. So you may be saying, well, why does that matter to me if I'm living in Pennsylvania? But earthquakes can happen anywhere, because there are smaller faults scattered throughout the interior of our continental masses. And we had one recently that affected our area here at Slippery Rock. So this was the 2011 East Coast earthquake. This was a 5.2 magnitude earthquake. So it was big enough to really be felt. I remember that I was at home. This happened in August. So I was at home in Pittsburgh and I felt the shaking. And I thought that this was something that happened to some construction that was going on in the house that was just up the hill from where I was. There are people working on that house there, and I thought, oh my gosh, did like the house fall down or something and cause that shaking? It wasn't until I got online and started looking at what other people were saying that I realized we had felt an earthquake. So it was strong enough that I really felt it, and it disrupted what I was working on. And so you can see from the map there, the epicenter of this earthquake was in the town of Mineral, Virginia. So a little rural town in Virginia where the yellow star is on the map, but all of the green dots show places where people felt this earthquake. So you can see it was all over the East Coast and even up into Canada. So I felt it in Pittsburgh. It was felt at Slippery Rock. And in fact, it actually damaged the south wall of the Spots World Cultures building. So that wall of the building started to essentially crack away from the rest of the building as a result of that earthquake. And they had to spend a bunch of money to basically bolt the wall back onto the building because it was causing a lot of problems. It also damaged, there used to be a bridge from the parking lot by the field house across to the top floor of Spots. So if you were coming and going from upper campus to a class on the top floor of Spots, you didn't have to go all the way down to the first floor doors of the building and then back up. You could take this little bridge that went across there into the top floor of the building, but that bridge was damaged in this earthquake, and they ultimately decided that it wasn't worth the cost of replacing it, so they just got rid of it and bricked over what had been the door on the outside of the building. So that earthquake is 5.2 magnitude, and its effects spread even all the way out to Slippery Rock's campus. So we can experience earthquakes even if you're living here in the East Coast of the United States, but obviously if you dream of going to live in California or Seattle or something like that, you're going to have even more encounters with earthquakes. Okay, so earthquakes are one of our major tectonic hazards. The other major one is volcanoes. So volcanoes are places where molten rock comes to the surface. So when molten rock comes out of the interior of the Earth onto the surface, we get a volcano. And we get different kinds of volcanoes depending on the chemical composition of the lava. So the molten rock that's coming out, depending on its chemical composition, it may be more or less viscous. So viscous is the thickness of a fluid. So if something is highly viscous, so it's very, very thick, moves very slowly, it's going to trap a lot of gases. So you're going to have a lot of bubbles of gases trapped in that lava. And so those bubbles are then going to burst, and you're going to get this explosive kind of eruption. And that's what you see in the upper picture. That's the eruption of Mount St. Helens in Washington State. So that eruption was hugely explosive and blew the whole side off the mountain. You had this gigantic cloud of ash going into the atmosphere that you see there. It looks almost like a mushroom cloud from a nuclear explosion. So Mount St. Helens had very viscous lava, so it had this very explosive kind of eruption. On the other hand, if your lava is less viscous, it's thinner, it's runnier, then those gases are going to be able to escape without causing this big blow up. And so you're going to get what we call an effusive eruption. So an effusive eruption is when the lava just kind of flows out and dribbles down the side of your volcano. And you can see that in the lower picture, which is of, I believe that's Kilauea, one of the volcanoes in Hawaii. So Hawaii is known for having these effusive eruptions where it doesn't blow the mountain up like Mount St. Helens, but the lava just flows out because it's very liquid, it's very runny and thin, and so all the gases are able to escape more easily. And so that's kind of a continuum. So any given volcanic eruption will be somewhere along this continuum from an explosive to an effusive eruption, and a particular volcano, depending on what kind of molten rock is feeding into it, could alternate different kinds of eruptions. It could sometimes have explosive, sometimes have effusive eruptions. And this gives me an opportunity to share one of my favorite geology memes here, because I've been talking about lava when I talk about the molten rock that has come out to the surface of the Earth, and we call it magma when it's still underground. And that's the only difference between lava and magma. Lava is when it's on the surface, magma is when it's underground. And so you see this tweet here from Thomedy Psi, where the devil says, "And this is the lake of lava that you'll be spending eternity in." And then the person replies, "Actually, we're underground, so it would be magma." And the devil says, "This is why you're here, you realize." So even if it condemns me to hell, I will be pedantic about the difference between lava on the surface, magma underground. So if we look at where volcanoes are found around the world, we find a pattern very similar to the earthquake pattern. So you can pull up the PowerPoint and compare this map to the earthquake map and to the tectonic plates map, and you find volcanoes mostly found along plate boundaries. So we've got a few that are scattered in the interior of plates, and we'll talk about those in a second. But most of our volcanoes are forming these nice little lines that follow the edges of our tectonic plates. Because when you have a plate boundary, that is, number one, going to make it easier for magma to rise to the surface and form a volcano, but also the processes that are happening at those plate boundaries particularly at the convergent and divergent plate boundaries, are going to drive the formation of volcanoes. They're going to produce the conditions under which volcanoes are going to occur. So here's our plate boundaries diagram, again, that we looked at earlier. And so I now want to focus in on what's happening at some of these boundaries. So we talked a little bit about divergent boundaries earlier in the lesson. So you can see that there. It's labeled as the ocean spreading ridge or divergent plate boundary on the diagram. And so there we've got our plates pulling apart from each other. And so we've got molten rock coming up from the asthenosphere to form new lithosphere to fill in that gap as the plates move apart. And so if you've got molten rock coming up out of the Earth onto the surface, you've got a volcano. So we get volcanic activity happening at these mid-ocean ridges where our divergent plate boundaries, we've got plates pulling apart from each other, and molten material from the asthenosphere comes up to replace it. Then to either side of this diagram, we see places where one plate is being pushed down underneath another plate. We call that process subduction. You can see it labeled, the subducting plate is labeled on the map there. Subduction, where one plate is pushed down into the asthenosphere underneath another one, happens at convergent plate boundaries. We've got two plates being pushed together. One of them will get pushed down into the asthenosphere, and as it gets pushed down into there, it's going to melt. Right? Our high temperatures in the asthenosphere that keep the asthenosphere molten are going to melt away that rock from the lithosphere that's getting pushed down into it. And that molten rock is now going to try to come back to the surface. It's made out of the chemical materials that are part of our surface rocks, which are lighter, and so they want to come back up to the surface. And so once they're melted, they're going to start flowing up through any little cracks they can find. And so we're going to get chains of volcanoes alongside places where a plate is being subducted, where it's being pushed down into the asthenosphere. And so that chain of volcanoes may take the form of volcanic mountains on the land. If the other plate, the one that's not subducting, has land on it, is a continental crust area. Or we could get a chain of volcanic islands if the plate that's not subducting is oceanic crust. So we get a string of volcanoes there, and they get tall enough to poke up out of the water, and we get volcanic islands. So if we look back at our map here, if we look at the Americas, we can see there's volcanoes all down the west coast of North and South America. So there we've got the plates that form the floor of the Pacific Ocean. So that's the Pacific plate, and then also the Nazca plate to the south. These plates are being subducted underneath the North and South American plates. They melt in the asthenosphere, and that molten material returns to the surface in the form of these volcanoes. So Mount St. Helens that we were looking at earlier in Washington State, along the west coast, it's being fed by the subduction of the Pacific plate underneath the North American plate. Other places, we can see these volcanoes on islands. So you can see the Caribbean. We've got this string of small volcanic islands that forms in the Caribbean. So these are islands like Martinique and Dominica and Barbados. All these little Caribbean islands, they're volcanoes. They're basically a chain of volcanoes that's forming as the South American plate subducts underneath the Caribbean plate. So there's a little plate that forms the floor of the Caribbean Sea, and it is converging with a piece of the South American plate, which is getting subducted, turns into magma, comes back to the surface in the form of these volcanoes. We also see volcanic islands in places like the Philippines, Japan, Indonesia. All those places you can see chains of volcanic islands being formed by subduction of one plate under another. So then what about those volcanoes that are kind of scattered in the middle of some of our tectonic plates? Those are caused by something called a hot spot. So a hot spot is a plume of magma that rises up from the asthenosphere. So within the asthenosphere, we can get these spots where we've just got a bunch of magma trying to come up to the surface. And figuring out exactly why these hot spots form, why they're located where they are, is an area of ongoing research. We don't have the answers to that nailed down, but we know they occur. That there are a bunch of these spots all around the world where, quite independent of plate boundaries and what the plates above them are doing, we've got magma trying to come up out of the asthenosphere and basically punch through to the surface. So whatever is above that hotspot will form a volcano. So we'll get a volcano above this hotspot. But then the plate is moving. All of our tectonic plates are moving, but our hotspots like to stay in one place. So that means eventually that volcano that was formed above the hotspot is going to get dragged away from it. And so that volcano is now going to go dormant. It's no longer being fed by the mantle plume at the hotspot, and a new volcano is going to form over the current location of the hotspot. So the hotspot is staying there, the plate is moving across it, and so we keep getting a volcano forms, then the volcano gets dragged away from the hotspot, new volcano forms above the hotspot. So we're going to get a chain of volcanoes. At one end of that chain is our active volcano that's being fed by the hotspot that's located right over the hotspot. And then going down the line, we get progressively older and older volcanoes. So we can see this in the case of Hawaii, which is one of the most famous hotspots in the world. The hotspot is currently under the Big Island. So our volcanoes of Mauna Loa and Kilauea on the Big Island are being fed by the hotspot. And we actually have a new volcano that's starting to form. It's still under the water, but off the southeastern coast of the Big Island, we've got Loihi, which is this new volcano that's forming as that spot on the Pacific Plate comes over that hotspot. So those are the volcanoes in Hawaii that are actually active, that actually have eruptions going on. But if we go down the chain, right, we see that the Big Island is, up to 0.7 million years old. Then the next island in the chain, Maui, is about 1.3 million years old. Molokai is 1.8. Oahu is 3.4 million years ago. So they're getting older and older the farther we go from the hotspot. So that means 3.4 million years ago, Oahu was directly over that mantle plume and was being formed by that volcano. And then Molokai, Maui, Big Island didn't even exist yet. They were just the ocean floor. But then the Oahu volcano got dragged off of the hotspot, and it is no longer actively erupting. Instead, it's starting to erode. So the other thing we see is not only do the islands get older as we go away from the hotspot, they also get smaller. So you get smaller and smaller islands going away from the hotspot until finally they're so small they've been eroded down so they no longer stick out of the water. And so then we get what are called seamounts. So a seamount is a extinct volcanic island that has been eroded down so that it doesn't stick up above the surface of the water anymore. And so as we got more data about the floor of the ocean, the topography of the ocean floor, we came to realize that the Hawaiian chain of islands, if we include seamounts in it, stretches all the way to Siberia. So we've only got a certain number of islands that we can see above the water, but we've got seamounts that continue all the way out to the edge. And so that shows us that the Pacific Plate has been moving across this hotspot for a very long time. The oldest of the seamounts, when we get all the way out to the edge of the plate, is about 80 million years old. So 80 million years ago, that part of the plate was what was over that hotspot. And it may have been going on for longer than that, except that that edge of the plate is a subduction zone. So the Pacific Plate is being destroyed at that edge there where it meets the edge of the Asian plate up there in Siberia. So there could be many, many millions of years older former volcanoes that are now lost because they've been subducted into the asthenosphere, they've melted, and that rock has returned to the surface in the form of volcanoes in Japan and Siberia. So this hotspot has been going and creating these volcanoes for a very long time. And you can also see that the shape of it, we've got a line and then it makes kind of a bend and changes direction. That indicates that the Pacific Plate changed direction at some point in history, specifically about 42 million years ago, which is about the age of the seamounts that are at that bend. So about 42 million years ago, the Pacific Plate went from going mostly northward, shifted to going more westward. And so we can actually trace that history by looking at the age and location of these extinct volcanoes that were formed by the Hawaii hotspot. So Hawaii is our most famous and clearest example of a hotspot, but we've got a number of other ones around the world. Two other ones that are good for you to know about are Iceland and Yellowstone. So in Iceland, we have a hotspot that in that case happens to be right now located along a plate boundary as well. So Iceland has two things going on. It's extremely tectonically active there because you've got the Mid-Atlantic Ridge. Iceland's located on the Mid-Atlantic Ridge, so you've got that divergent plate boundary going on, and you also have a hot spot right below it that is sending up a mantle plume. So Iceland has a sort of double whammy of tectonic activity at the moment. And then you have Yellowstone. So all of the interesting geological features of Yellowstone, the hot springs, the geysers, etc., that you might see if you go there on vacation, those are all driven by the heat from a hotspot. So we have a hotspot underneath Yellowstone. It is not currently actively erupting, but geologists are studying it, monitoring it, because if it were to erupt, it could have some pretty serious consequences to have a big volcano occurring right in the middle of North America. So all of the fun stuff that make Yellowstone a cool tourist destination is driven by this hotspot that sits underneath the middle of the North American plate and is fairly quiet at the moment, but could potentially erupt much bigger at some point in the future. Okay, so let's now look at the hazards that can be caused by a volcano. So the most obvious one, of course, is the flow of lava. So if lava is coming out of the volcano and running down the sides, you should get out of the way. Sometimes that lava is moving very fast. Other times it's actually moving slow enough that you can walk away from it. But in either case, if you know lava is coming, you should definitely get out of there. Don't risk it. There have been instances of tourists going to active eruptions in places like Hawaii or Iceland because they think it'd be cool to get really close to this lava that's flowing and like take a selfie. And people have gotten severely hurt or even killed doing that. So only trained volcanologists should approach an active volcano and try to, look at the lava. We also have pyroclastic flows. So this is all of the ash and rocks and things that get exploded out of a volcano, especially with a more explosive type of eruption, and those will fall down and run down the sides of the volcano as well. We also have toxic gases. So we mentioned that one of the things that causes the differences in eruption styles is the bubbles of gas that are trapped in the magma and that try to escape as it reaches the surface. And so these gases include things like carbon dioxide, sulfur dioxide, hydrogen sulfide. And so these gases can be very toxic if you are breathing them in the concentrations that you're going to get at a volcano, right? Like obviously there's carbon dioxide in the air that we're breathing all the time, but there's only a very tiny amount of it. If you are right by a volcanic eruption, you'll get far more CO2 in the air, and that can actually make it impossible for you to breathe. You could pass out because you can't get enough oxygen. There's too much CO2. And some of these other gases are very directly damaging to your body if you're breathing them in. So we get this flow of toxic gases coming out of the volcano as well. We can get acid rain and ash fall. So some of the material from the eruption gets blown up into the atmosphere and can travel a longer distance before it falls back down to the surface. So some of these materials, they get into the atmosphere and then they get absorbed into rain droplets that fall down, and they make that rain more acidic. And so we get acid rain, which can be very damaging to various living organisms that the acid rain falls on, as well as to things like buildings and other infrastructure. And we can get the fall of ash that was transported through the atmosphere and then eventually settles on places. And that's what the photo there shows you. That is actually a US military base in the Philippines that experienced a nearby volcanic eruption, and this thick layer of ash fell on top of all the buildings, and you can see that those buildings have just been crushed by the ash. So the weight of the ash that fell on those buildings just was too much and collapsed the whole building there. Volcanoes can set off forest fires. You've got all this very hot stuff coming out of a volcano. So if some of that gets in touch with some dried out forest areas, it can set off a forest fire. You can get lahars, which are mudslides. So that just is a word coming from Indonesian that means a mudslide. And so there are various ways that this could be triggered. So you could have mud and other sediments that are, on the sides of your mountains that get dislodged by the earthquakes that accompany a volcanic eruption. So a volcanic eruption is generally accompanied by a lot of shaking of the earth, a lot of earthquake activity that could just shake stuff up and cause it to slide down the mountain. You could have all of the heat from the volcano melt ice. So a lot of volcanoes are occurring in high mountain ranges where when the volcano is not erupting, it's very cold, you get ice forming, but you get all the heat from the volcano that could melt that ice, and that water could then saturate the ground and cause that to turn into mud that then slides down the hill. You could also get things deposited from the volcano, so these pyroclastic flows, the ash and so forth, it gets deposited somewhere, and then you get heavy rain following the volcano. And that rain saturates your ash and pyroclastic material and causes it to slide down the hill. So there's a number of different ways that you can trigger a major mudslide, but those happen. And because those can be delayed, right? If it's a situation where, for example, you've got a whole bunch of ash that is sitting there, and then sometime later you get a big rainstorm that saturates it and makes it slide down, that could be days, weeks, months after the volcanic eruption. And so those can sometimes catch people really off guard because they think, oh, the volcanic eruption is over, we can go back, try to rebuild things, try to put our lives back together, and then they get hit with this giant mudslide that was some distance after. And then at the global scale, volcanoes can actually cause a cooling of the climate. So volcanoes release CO2, which we will get into in later lessons about how that is a greenhouse gas that warms the Earth. Right? That is one of the flows that you looked at last lesson, flows from the geological stocks of carbon into the atmospheric stock. But at the same time, volcanoes are also putting out ash and sulfur that block sunlight. So they filter out the sun's rays, reflect them away from the Earth. So in the short term, the year or two after a major volcanic eruption, the net effect of that volcano is actually cooling the Earth. And so there have been some major volcanic eruptions in history that have caused significant global cooling for a year or two, blocking out the sun, causing harvest failures and famines and so forth on the opposite side of the Earth from where that volcano was. So there can even be these climate effects that can hit the entire world, not just the location right in the pathway of the volcano. But then I also mentioned the last bullet point there, one positive thing that we get out of volcanic eruptions is new soil. So all of this material that the volcano is bringing to the surface eventually goes on to form the basis of very fertile soil. There's a lot of important nutrients that are brought back to the surface through volcanic activity. And so we often find large numbers of people living right in the shadow of active volcanoes because that soil is so fertile. So a place like Indonesia, an extremely volcanically active place, the Philippines, Mexico, lots of areas of the world that are very volcanically active, but also have very fertile soils because of the volcanic ash and other materials that bring nutrients out of the earth onto the surface. So it's kind of a trade-off living next to a volcano, that you'll have a better productivity on your farm, but you need to watch out when the volcano actually erupts. Okay, so having looked at these two different kinds of tectonic hazards, I now want to talk about how they harm people and which people they harm. So there's an expression that people that research natural hazards often use, which is to say there's no such thing as a natural disaster. So again, in everyday speech, we talk about natural disasters all the time. We call a volcano eruption or an earthquake a natural disaster. But researchers that work on these things will say there's no such thing as a natural disaster. And so here's what we mean by that. A disaster is the loss of things people value. So a disaster is a massive loss of things that people care about. So that includes people's lives, includes property, it includes infrastructure, it includes communities, any of the stuff that we care about. If we lose a whole bunch of it, we've experienced a disaster. And a disaster occurs at the intersection of a hazard event and the vulnerability that people have to that hazard. So something like an earthquake or a volcanic eruption is a hazard. So it's a, in this case, natural event. There are also technological hazards like a nuclear plant meltdown, but if we're focusing on natural hazards, those are things like earthquakes and volcanoes that have the potential to damage things people value. But how much damage there's going to do depends heavily on how vulnerable those values are. And vulnerability is something that we can control. Who is more vulnerable to certain hazards depends on what human societies do, how we organize and build our human societies. It is not a natural thing. So that's why we say there's no such thing as a natural disaster, because a disaster requires the intersection of a natural hazard event with human-created anthropogenic vulnerability. So here's an illustration using earthquakes as our example. We got this like very clear demonstration of the importance of vulnerability in creating a disaster in 2010, where we had two major earthquakes happen in the Western Hemisphere. So in January of that year, we had an earthquake in Haiti. And so that earthquake was a 7 magnitude. So that's a pretty big earthquake. So we had the 7 magnitude earthquake in the country of Haiti, and there are an estimated 230,000 people that were killed. So just massive loss of life, and then a lot of longer term repercussions because so many houses were destroyed, so many people's livelihoods were destroyed by this earthquake. So the deaths alone don't even give you the full scope of the damage done by this earthquake in Haiti. Then a month later, we had an earthquake in Santiago, Chile. And that earthquake was an 8.8 magnitude. So if you remember, we said our magnitude scale is logarithmic. So an 8 magnitude earthquake would be 10 times as much energy as a 7 magnitude. And then a 9 magnitude will be 100 times as much energy as a 7 magnitude. So this earthquake in Chile was almost 100 times more energy involved than the one in Haiti. And it struck near Santiago, the capital of Chile, where a lot of people were living. And yet, despite being a massively larger earthquake in terms of the scale of the hazard, the scale of the energy released in the shaking of the earth, only 531 people were killed in Chile. So how is it that a smaller earthquake in Haiti killed 230,000 people, whereas the larger earthquake in Chile only killed 531? Well, it's the difference in the vulnerability of the people in these two countries. Haiti is one of the poorest countries in the world. So the people in Haiti were extremely vulnerable. They, for example, had not been able to afford to build their houses according to our best standards for earthquake-proof engineering. A lot of the houses that people who died in the Haiti earthquake were living in were basically shacks that they had slapped together from whatever materials they could find because they just didn't have the money to build a decent, well-engineered house. Whereas Chile is a middle-income country. So Chile is not as rich as like the United States or Britain or something, but they are certainly not as poor overall as Haiti. So buildings in Chile had been built up to these earthquake proof standards. So there was damage done, right? And 531 people did still die. There were still a bunch of buildings that were damaged or collapsed, but not nearly on the same scale as you saw in Haiti. Chile also, because it's a richer country, had better emergency response abilities. So they were able to get rescue teams in to pull people out of the rubble. They were able to get food and water and shelter to people that had been displaced by the earthquake much quicker and on a much larger scale than Haiti was able to pull off. So the difference in vulnerability, the difference in how people were living, the resources they had access to, is the real explanation of the difference in the death tolls and the other destruction that happened in these two cases. Neither of these would have happened at all if it hadn't been for a hazard event. The earthquake still needs to happen. Nature still needs to make its contribution, but the scale of the disaster that results when we have a natural event like an earthquake depends so heavily on the vulnerability of the people in that place. And as a rule, those who are already worse off in the society as a whole, so that includes people who are poor, women, racially marginalized groups, disabled people, right? Anybody that is worse off in society before the hazard event happens is almost always going to be more vulnerable to that hazard and is going to suffer a greater disaster. It's going to be more likely to be killed, more likely to lose property, more likely to lose jobs, etc. So our social inequalities shape our vulnerability, which shapes the outcomes of natural hazard events like earthquakes and volcanic eruptions. So I will leave you with that thought and see you again next week.